So here we have an electric field problem where we are trying to determine the electric field produced by two different charges. Specifically, we want to know the point where the resultant field intensity is zero, essentially where they cancel each other. So the equation that we're going to use is the electric field is equal to KQ over R plus KQ over R, where the Q's, this should be Q1, this should be Q2, are the individual charges, and R is the distance from that charge to the point where we are measuring the field. So we don't know exactly where it is, but we're going to have to generalize it with one variable so we can solve it. And we want that to equal 0. Now, I drew the scenario here. We have a +4 charge and a negative 1 Q charge. And then we have this, this distance of A separating them, okay, which is indicated by the red. So I put 3 different locations down. We're going to determine which of these locations is most likely. Either it's to the left of the, it's on the side of the +4 charge, it's in between, or it's to the right of the negative Q charge. So right away we can tell it's not going to be in between. And the reason it won't be is because no matter where you are in between, this charge would have an electric field going to the right. This charge would have an electric field going away from it. Remember that electric fields go away from positive charges and towards negative charges. So no matter where you are in between them, you're never going to get a cancellation. They'll always add to each other. Now, if you go outside, you get both cases. So if I go to the left here, I have the +4 charge causing an electric field going this way, and the negative Q charge causing me to come to the right. Whereas out here, I have the negative Q charge pushing me to the left to go back towards, remember they end on negative charges, and then the +Q charge is pushing me away. So on either side, I have a possible cancellation effect. The question is which one is more likely or which one's even possible. And I'll tell you right now, it's not this one. And the reason for that is that the charge is stronger on the near side, meaning that no matter what, wherever you place this point, exactly whether it's, however far away it is to the left of the +4Q, it's going to be closer to the +4Q by a distance of A, which means that it'll never cancel out because you have a stronger charge and you're always closer to it. Here, you are closer to the weaker charge, meaning that you can make up for the difference in charges with distance. So we know that it's going to be over here somewhere. Now, what I'm going to do is I'm going to say that the distance from negative Q to that point is X. And this X is what we're going to solve for. We don't know A. But we can find X in terms of A. So maybe it'll be 1/2 of A or something like that. So let's insert our values then. We know that this is equal to 0. So K times Q1, we'll say that's the 4Q. So we get 4Q over R1 squared. So R1 is the distance from 4Q to this point that we marked where we're expecting it to be. That distance is A plus this X value that I wrote here. So we have A plus X squared, the full distance from the +4 charge to this spot. Then we have a minus because of the negative Q. Minus KQ over R2. R2 is just X because it's just the distance from that charge to here. So we can say that this is X squared and that equals 0. Now what we're going to do is we're going to add this over. So then we get 4KQ over A plus X squared equals KQ over X squared. And notice that the K and the Q can cancel. And what I'm going to do is cross multiply all in one step here. So the KQs are gone. This is essentially a 1. That's essentially a 4. I'm going to multiply the X squared over here and the A plus X squared over there. So what you end up getting is 4X squared equals A plus X squared. Sorry, A plus X squared, I should say. Okay. And then what you can do is you can square root that. On the left side, you get 2X, and on the right side, you get A plus X. Now, doing a square root is actually kind of interesting because you get a plus or minus, and you could theoretically have different negatives and stuff here. But remember, we are assuming we know exactly where this is happening. We know it's happening to the right, so we're assuming A and X are both positive, which means we're not going to allow for any negatives here. If we did have a negative, we would have to say this is either negative 2x. Actually, yeah, let's go through all four of those options. So if we assume everything is positive, we subtract the x, and you get that x equals a. All right, that's if you assume everything is positive, which is the simplest result. Now let's assume that the negative 2x, it's negative 2x equals ax plus a. So we say that that right side's negative. This doesn't work because when we subtract the x, we get negative 3x equals a. So this is all positive, and then negative 2x. So then if we assume we have a negative a plus x, which is the whole right side, then what we get is 2x, which is positive now, equals negative a minus x. We add that over, we get 3x equals negative ax. So once again, these don't make sense because we're not allowing negatives to occur. This one does make sense. This is our potential answer. And then we can do both negative. But here's the thing with both negative. If we say negative 2x equals negative a plus x, if they're both, that's the same thing as saying they're both positive because we can just cancel them. So if they're different signs, it doesn't work. If they're the same signs, we do get a simplification, which just means that this point has to be the same distance they are apart to the right of negative q. So essentially the distance from 4q to this point is 2a. The distance from negative q to this point is a. Hope that helps.